So first of all, thank you so much for attending this presentation. Thank you, Stefan, for the invitation. I'm very honored to speak about my project. Today, I'm going to present only the initial stage of my research project, devoted to implementing Bayesian networks for modeling stress corrosion cracking of duplex stainless steel in downhole or production environments. So let's go through. Let's go through the introduction just for you to be familiarized with the stress corrosion cracking production or downhole environments and also duplex stainless steel. So, well, stress corrosion cracking is essentially a predominant threat for engineering tools for the components comprising the production equipment for oil and gas. And it's also one of the forms of environmentally assisted cracking, which is essentially driven by the aggressive characteristics of this environment. This is the constant exposition to highly corrosive species such as chloride, elemental sulfur, hydrogen sulfide, principally, and also the exposition to elevated pressures and temperature. In here, I'm referring only to very challenging fields where the temperature condition and also the pressure condition can reach more than 206 megapascal for the pressure and 230 degrees in temperature. Over here, you can see some of the forms of stress corrosion cracking. We have different ways of stress corrosion cracking and also for different materials. Now, the material of our interest, duplex stainless steel, is essentially used to improve the integrity of production equipment and transportation facilities. And this is given their high corrosion resistance and also their magnificent mechanical properties. Some of the characteristics, duplex stainless steel contains from 22 to 25% of chromium. This is weight percentage with some additions of nickel, molybdenum, and also nitrogen and tungsten. In this table, you can see one of the chemical composition of the samples we are using in this project. And this chemical composition is what actually promotes the formation of a passivation layer. It's a small layer, very rich in chromium oxide that provides to the material its corrosion resistance. That's why duplex stainless steel exhibits low corrosion rates in the presence of CO2, hydrogen sulfide, at temperatures typically lower than 100 degrees. Now, with regards to the mechanical properties, principally the yield strength varies from 450 to more than 1,000 megapascal, depending on the heat treatment, being then this material ideal for deep reservoir applications. Now, what you need to know more or less the behavior about stress corrosion cracking for this material. And well, it's proven that it's affected by the synergism between chloride and hydrogen sulfide, essentially the chloride ions, in addition to the temperature conditions. You can see in this picture a sample of duplex stainless steel when it's exposed to a testing solution of sodium chloride with a concentration of 100 grams per liter at room temperature, which is also exposed to a gas mixture with a partial pressure of hydrogen sulfide equal to 0.5 bar. Now, you can see the sample survived. It not presented any damage by the stress corrosion cracking. Nevertheless, as these experimental conditions increase, the damage by stress corrosion cracking becomes more severe. Actually, in this picture, you can see the initiation of a stress corrosion cracking, which is a localized form of corrosion called pitting. And pitting is what eventually will develop cracking until leading ultimately to the failure of this material. Now, the main problem with duplex stainless steel in the industry is that the performance of these alloys are not well documented in standards. The main standard for oil and gas applications in here has established, well, a limit for duplex stainless steel, any kind of duplex stainless steel, when the environment presents a partial pressure of H2S close to 0.2 bar. This is the standard. And not only that, this limit is associated also with any kind of combination of temperature, chloride, or pH. So just based on great numbers, significant number of investigations, we know that this limit can be overly conservative. And we are studying this material not only because it's conservative or for safety reasons, also for a reason of cost, because the next alloy to choose when we have a higher concentration of hydrogen sulfide are nickel-based alloys, and the utilization of nickel-based alloys can be extremely expensive. To further exemplify this particular phenomenon, this limit, I picked up some data points from relevant literature. And then I correlate the temperature, the hydrogen sulfide, and in this graph, the color is indicating when a sample of Duplex stainless steel did not suffer stress corrosion cracking. The red points are indicating when essentially a certain degree of stress corrosion cracking occurred. And you can see the limiting here established by the standards, and how most of the points, most of the samples, can comfortably withstand these high concentrations of hydrogen sulfide. Maybe just for this data set, I just calculate the mean, and for the red points, possibly the maximum limit can be established at 0.8 bar. The main problem here is in between, where some of the samples can survive, some of the samples are failing by stress corrosion cracking, and essentially we cannot distinguish what is happening in this system. Some of the reason is because the high variations of the chlorine content, ranging from 2,000 parts per million, and also the pH is changing considerably. But another factor can be the full chemical composition of the material, which can change from provider to provider. So what we have in here is a multidimensional space, a multidimensional system, where it's extremely difficult to determine the interplay of these numerous factors. And in this project, what we are intended to do is developing a model for estimating the susceptibility of stress corrosion cracking, specifically for these materials. And our main framework is simulating the pit to chronic transition process. As I mentioned before, stress corrosion cracking almost all the time initiates from pitting, from a localized form of corrosion, which eventually will evolve to crack. I will explain this process a little bit more in the next slides. And this is why, and the numerous of variables in this system, I choose the utilization of probabilistic graphical methods and specific Bayesian networks. I just listed some of the reasons why I chose this modeling approach, principally because of the stochastic nature of the failures by stress corrosion cracking and the utilization of real data. Many of the applications for modeling this particular corrosion phenomenon employs other modeling techniques such as atomistic simulation, finite element methods, and also phase field methods. But it's very difficult the transition between those scales. One of the other reason is because we can incorporate several sources of information. This is really important. We want to exploit this advantage because in comparison to other alloys used in oil and gas, such as the regular stainless steel or carbon steel, Duplex stainless steel has been barely studied. So there is information, but never have been put together in a single framework. The reason as well, other reason is also, the advantage of reasoning backwards, which, experimentally, we're going to see if pitting or stress corrosion cracking happen, but we want to analyze the possible pathways that can lead to that result we are observing. So Bayesian networks in this case can help us to that task. And lastly, more importantly, I think, is that this concept, this probabilistic modeling approach, can be applied even when the data is ambiguous or incomplete. And this is the case, and I think this is the most challenging part of this project. Now, regarding the data that we are going to use several sources of information, numerical outputs. We are using atomistic simulation for certain variables for certain nodes of the network that can be only measured by such technique. Some other experimental results that we are conducting right now. We are collecting that data, and also data from the literature. Evidently, we need the expert knowledge as well. We have in one of the best laboratories about corrosion in the world. And this is the way we are going to work for establishing the structure for the Bayesian network for this model. Now, this is a more detailed representation of the P2 transition, of the framework we are trying to transfer to a Bayesian network. As I told you, this particular layer possesses a passivation layer. And in order for the pit to grow, to start, this passivation layer, this passive field should break down. Once this passivation layer breaks down, then you can see the initiation of the pit. Now I'm going to show you a video. Just give me 1 second, and maybe you can notice how is the process. So in here, you can see the formation of the pit. These are the dissolution process of the metallic material and the propagation of the pit. The morphology in here is very important because this kind of surface flows tend to concentrate stresses around the pit. So this concentration of the stresses is essentially associated with the geometrical form of the pit, which is like a fatigue phenomenon that induces the beginning of cracking at the bottom of the pit. The second process, really important and very difficult to measure, is the local chemistry into the pit, where the pH can change and induce an hydrogen reduction reaction. This cathodic reaction results eventually in the embridlement of the material. It's a nitrogen embridlement process that reduces the mechanical process, the mechanical properties of the material eventually in this part, and also enhancing the crack propagation of the material and eventually the failure. Now, it is pertinent to say that, well, in here I noted the conduct criteria. The conduct criteria is something very important because the stress corrosion cracking requires pitting. Nevertheless, not all the pits in a sample of duplex stainless steel can evolve to cracks. That will depend on the concentration of the stresses, and also that will depend of the corrosivity in the environment. And you can see some picture in here about pitting, how it's evolving to cracks. Now, well, in here you can see the stresses that are subjecting to the sample. Well, transfer to a Bayesian network is a conceptual design that we are using as the main guidelines for looking for information in the literature. And well, this is only based on expert knowledge. This is the theoretical framework that we want to interconnect. In here you can find out the environmental factors leading to the pitting corrosion. In here we can find something, some electrochemical metrics that we are using to monitor the formation of pitting. In here, we can find some nodes associated with the local chemistry into the pit draw rate, the cathodic reaction and the formation of hydrogen, and the influence of stresses in this part leading to the crack propagation. Now, once more, this is a theoretical framework, is what the expert is expecting to see. Nevertheless, in reality, once we go through the literature, we cannot maybe find all those variables. And so far, we have generated a database containing more than 2,000 records that can report the chemical composition of several duplex stainless steel alloys. We have the environmental parameters, Also, we have logical and categorical data reporting pitting or stress corrosion cracking, but also, and unfortunately, we have a significant volume of missing information. And the reason of this is because some investigations are only associated or focused on pitting corrosion, while others are only focused on stress corrosion cracking. Some other investigations are not interconnecting these two phenomena, and well, others, they can do that, but it's very expensive. You need to know that one experiment, either for pitting or stress corrosion cracking, can last days, and it's very expensive as well to emulate, to work with both phenomena. And also the experimentation for pitting or stress corrosion cracking involves different experimental setups and samples. We are trying in this case to interconnect to different scales, something micro and something macro. Nevertheless, before starting the development of the Bayesian network, we need to analyze our data. And in order to avoid certain outliers in our data set, because the process of data extraction, well, maybe it's very difficult to determine row by row which of those data points can work for our model or not, and also which of those data points can be suitable for our samples. Now, after running hierarchical clustering, we found out 5 different clusters. And the 3 first clusters, once we obtain the result, we look into the information and the characteristics of these clusters, and we find out that they have a dominant alloy. And these alloys are presenting very similar chemical compositions, just something different in certain addition of molybdenum or of nitrogen, but essentially they are showing certain similarity. Also, the environmental conditions for testing it are kind of similar. And while the 2 last clusters, well, these alloys are considered as stronger because they have a higher degree of nickel, chromium, more additions of copper, of tungsten, and also they have a significant volume of missing information. So far, we consider these particular clusters as outliers that are not adequate for our samples with which we are going to run experiments. Now, once we have this data set, we are going to Bayesian Lab, and maybe I am the most recent customer of Bayesian Lab, so evidently I'm not using properly the tools. But I'm just showing this slide because this is the way I'm working right now. Or I work at the beginning, and this is what you face. We are having here different variables, the most common variables reported on the literature. We don't know how to interconnect it. We have expert knowledge, of course, but the problem is that nobody has intended the interconnection of these 2 phenomena only using data. Some of them have postulated more models, but it's very difficult to determine how to connect all the nodes. So what occurs to me is just providing to the experts certain skeletons, certain first approach of the structure, just certain alternatives, and then they can move the rows, they can modify the networks, and also determine which nodes we can use, which of those we can discard, and also, according to our experimental work, what other variables we can interconnect. And it occurs to me using a different, I mean, I know that we can run that imputation using Bayesian Lab, but just for pre-solving the data set, I use a different data imputation technique. In this case, I use random forest imputation. And the reason why I use this particular algorithm is because the random forest, used properly, can help us to distinguish, can help us to provide certain variability to our data set, even when we are not completely sure about the relationships between the variables. And the other characteristic is that we can work with both numerical and also categorical data. For those that are not familiarized with the algorithm, essentially the algorithm recognizes the empty values. It starts with imputation of the mean and also the mode for the categorical values. Then an army of decision trees establish a prediction. The average of all the predictions is imputed just at the beginning for the numerical part, and then a cross-validation process determines the most suitable label for the categorical part of the dataset. So this is another image about the dataset. Just I select 200, almost 300 data points presenting similar environmental conditions. And you can see the empty values over here. Some of them, as you can see, are reporting stress corrosion cracking, pitting, but nothing in the middle, nothing about the electrochemical parameters, nothing about the pit. This is the variable of pit grout rate. The uniform corrosion rate is associated only with the loss of material, and the load, which is the stress, and also time to failure. Once we run the algorithm, we found out the solution of our data set. This is only the first trial that we intended. And you can see that the algorithm can determine when we have pitting, stress corrosion cracking, and when we don't, logically. So this is the first trial. Another analysis that we run is the principal component analysis, just to examine the relationships among the imputed values. And what we are expecting to see is something similar to this. In this row, in this part, we have the CGR that stands for the crack growth rate, which is presenting certain connections with the three main variables we're expecting to see: hydrogen sulfide, chloride, and also the stress, the load applied. So all the data points in here are presenting a stress corrosion cracking due to these three parameters. The rest of the parameters over this quadrant, apparently they presented stress corrosion cracking and also pitting, but the main reason presumably can be the temperature and also the pH. Those data points that did not suffer stress corrosion cracking, looking into the observation, are associated to different duplex stainless steel alloys presenting higher mechanical properties. Apparently, this is a reasonable approximation of what we are expecting to see. With this solved data set, we are using Bayesian Lab just to, let's say, propose a different initial network. And this is the result. I tried several times. Recently, I learned, well, I was in the introductory course of Bayesian Lab, and I started running some structural learning algorithms. And we elucidate a more organized structure. What it was something surprising at the moment is that these three parameters show certain connection with environmental factors over here. Now, we didn't notice this because essentially these parameters are coming from electrochemical tests. When we are monitoring pitting corrosion, we have this kind of polarization curves. And the corrosion potential over here, which is the node here, is the corrosion or the potential indicating the corrosivity of the environment that increase the current because we are having more, there are some electrons from the material that are being loose, and then the current increases. Then the current decreases because of the action of the passivation layer. Nevertheless, the potential is increasing. And at a certain point, the current starts to increase drastically. And this is when we know that that pitting occurs. This EBD that stands for breakdown potential is exactly the EPIT that we have in here, the pitting potential. And the other parameter, ERP, we call it repassivation potential because the current suffers this hysteresis loop. And that happens when the pitting propagation stops, the pit route stops. Now, we didn't notice this because we are using this logically in our experiment just to decide and analyze pitting. Actually, at the beginning, we were using pitting such as a naive structure, connecting these parameters to this pitting. But the structural algorithms show us that the most correct organization could be using these experimental parameters, deciding if pitting occurs or not. When we were checking just initially the discretization and the nodes, we select pitting, and also we select stress. We are checking that the movement of the corrosion potential are according to our knowledge, which is the case, and the pit growth rate also increases. More importantly, the stress corrosion cracking, the probability of stress corrosion cracking increases in this proportion. And this is because we are not testing some other parameters such as the temperature or the partial pressure of hydrogen sulfide. But if we have the stresses, it's very likely that the stress corrosion cracking occurs. So for us, it's just the initial structural design, which is used for the experts to modify and then creating or deciding which node we can include to this model. The work is not complete yet. Just we have determined partially the main skeleton for the network, but there are some other variables or other nodes that are going to be determined using experimental or simulation studies. In this case, the pit morphology and the pH into the pit are nodes that can be determined using experiments. Actually, we have a separate team running these experiments. The stress concentration, the hydrogen sulfide, the fraction energy, for instance, are nodes that are going to be determined using atomistic simulation. We need just to be careful about selecting the scenarios, the models, and the data points that we are going to simulate. And the last, well, these first two nodes, the elemental sulfur here and the incubation period, well, essentially we want to use the latent variable concept because it's very, well, actually there are no information about these nodes. We know that the influence of elemental sulfur is important for stress corrosion cracking, even more when the concentrations of hydrogen sulfide are considerably high, but there are no methods to determine this node. And the incubation period is more or less the same. The incubation period is a part of the time that the surface of the sample will not present any kind of flow. But even with when we are not capable of observe pitting, we know that the pitting is incubating into the material because of the gradual breakdown of the passivation layer. But so far, this is the beginning of this research. So the main takeaway of this presentation, well, is that we are trying to use the Bayesian network modeling for providing an explanatory framework of stress corrosion cracking of duplex stainless steel in this production environment. We are trying to exploit the advantage of this probabilistic approach to reconcile any possible information source given its limited amount. And we are trying to combine expert knowledge, experimental work, and numerical models. Moreover, we are also implementing unsupervised learning, hierarchical clustering, principal component analysis, for analyzing our data set, being careful about the selection of the data points we are going to use, and well, analyzing the coherency that we are trying to see in our data set. More importantly, well, the data imputation by a random forest facilitated just at the beginning the elucidation of the BN structure. We know that using Bayesian lab, this kind of elucidation, this process can be solved more efficiently using a more robust process, can be either utilizing the expectation maximization algorithm, or I have been reading about entropy-based models for handling missing information. So far, this is what we have in this project. We just passed the first suspension, my research proposal. So I have to acknowledge the SHIELD team in the Corrosion Center, my supervisor, Professor Mariano Yaruzzi, Dr. Sam Bakari, my direct supervisor, and also the SHIELD Technology Center at Bangalore. Well, thank you so much. I don't know if you have questions.